So what's the relationship between nonlinear optics and character tables? You've probably all seen character tables before, and they describe symmetry operations, in this case a twofold rotation about the z-axis, or a reflection about the yz plane, or the xz plane or the yz plane. And the two things we're going to be focusing on are the two that are shown and the one that isn't shown, which would correspond to the hyperpolarizability. So the linear corresponds to the transition moment, the quadratic corresponds to the alpha, whether it is the Raman, as in the case of vibration, Raman, yes, here is in the case of some frequency generation, or two-photon absorption matrix in the case of a second harmonic generation. So how are we going to build and connect the character tables that are most commonly accessible and understand how they play out in terms of the nonlinear optics? We're going to work through initially an example with C2V. And this is the character table for C2V, and we've got a C2 symmetry operation and two mirror planes, as I mentioned previously. I'll tell you what the final result is going to be, and then we'll see if we can figure out why and how we got there. But the idea is this. If we know, for example, in the case of some frequency generation, that the process in the numerator, or the resonant part, is given by this coherent combination of one photon absorption and an anti-Stokes Raman back down, then the first two indices, I, J, are going to correspond to, to the alpha. And then the rightmost index is going to correspond to the mu. And so if we look at this A1 transition, we can see that the mu has to be Z-polarized, and that means this K, corresponding to the transition moment polarization, must be Z, and that's why every single one of these three ends in Z. And then the left two can be either XX, YY, or ZZ, and that gives us beta XXZ, beta YYZ, and beta ZZZ. Now for the B1 transition, it's a similar analysis. We know that the rightmost index must be X, and the leftmost indices can either be XZ or ZX, and that leads to these two tensor elements, and this roughly equal sign accounts for the fact that most commonly the Raman matrix is assumed to be symmetric, and if the Raman matrix is symmetric, then these two tensor elements become equal. And we can do the same analysis to get the relationship for B2 symmetry. So in this case, it's fairly straightforward, and it really simplifies the number of tensor elements that have to be considered dramatically. Instead of all, 7 of them, we can reduce it down to either 3 unique elements in the case of A1, or just a single unique element for both B1 and B2 transitions. In the case of resonant second harmonic generation, where we're resonant at the second harmonic, it's this exact same analysis, only now Z corresponds to the first index instead of the last. So where did these relationships come from? How do we know, it will turn out to be useful later on, how do we know that these correspond, the X, Y, and Z? How do we identify that those were the tensor elements associated with each of these particular symmetry classes, irreducible representations? And the way that we're going to do it is to take advantage of these symmetry operations. We're going to formally define them as symmetry operations. And let's see what that means. What does a C2Z operation do? Well, it's a 180-degree rotation about the z-axis. That takes x into negative x, y into negative y, and z stays z. So that matrix corresponds to negative 1, 0, 0, 0, negative 1, 0, 0, 0, 1. So that tells us that for the C2 operation, you're either going to have a value of 1 or negative 1 upon operation of this symmetry. So if we look at the transition moment as x, y, and z, you can see that if you leave something unchanged, if it has an eigenvalue of 1, then the performance of this symmetry operation will recover a value of 1. And only mu z has that appropriate symmetry, which is why it shows up in A1 symmetry. For both B1 and B2, if you perform a C2 symmetry operation, you are going to, for mu x, mu y, mu z, your new vector is going to have a negative sign for both the mu x and mu y. So those two invert in sign for the C2 symmetry operation, which gives you that negative 1 there. The sigma xz gives you a matrix that looks like it inverts the y, so it's going to be 1, 0, 0, 0, negative 1, 0, 0, 0, 1. And that's how we can write the symmetry matrix for sigma xz. Sigma yz is the same thing, it inverts the x, except. So those are the three symmetry matrices that we're going to use to describe these symmetry operations. This helps us identify what the non-zero elements are for the linear part. How do we get the quadratic part? Well, it's the same basic idea, except we do a Kronecker product. And I'll show you an example here for the YZ symmetry operation. So if we, for the Kronecker product, I'm going to take this matrix and multiply it by -1, and then stack that with this matrix multiplied by 1, and then this matrix multiplied by 1 again. So that gives you a 1, -1, -1, -1, 1, 1, -1, 1, 1 along the diagonals and 0 every place else when you multiply this Kronecker with itself. And this is going to give us the non-zero elements inside the quadratic term. So if we have an eigenvalue of -1, which of these recovers a -1 value? You can see that that's going to correspond to mu xy. This actually shouldn't be mu, these should be alpha. Alpha xy, alpha xz, alpha yz. All of these ones in circle correspond to a -1 upon performing the sigma yz symmetry operation. If we go to sigma yz, that's going to be this set of combinations, right? That's going to be everything with an xy or an xz in it, and those are 4 of them. So that limits it down. The sigma yz symmetry operation tells us that we've narrowed it down to this combination in terms of how these representations transform upon this symmetry operation. If we then look at another one, for example, if we just play out all of these, this is the one we started with before. This is for the sigma yz. If we do the C2, then that gives us, let's see, that should give us this. Yeah, C2, no, this is I'm just going to fix this. So let's next consider how this plays out for the quadratic part. And how do we get there? It turns out it's pretty straightforward. We do the exact same trick we've done previously for the overall symmetry. We apply the symmetry operation as a Kronecker product to alpha. And this is what we get for, let's consider that specifically the case of B1 symmetry. So we know for B1, if we look at the sigma yz operation, that's this one, we should have an eigenvalue of -1. In other words, performing that symmetry operation should invert the sign of alpha. And which of these do that? Well, how do we make this? We make this from the Kronecker product. Let's explore this Kronecker product very briefly, just to refresh your memory. For this case, we're inverting about the yz plane, so that's going to give us -1, 0, 0, 0, 1, 0, 0, 0, 1 as our symmetry matrix. And we're taking the Kronecker product of this with itself. So if I take -1 times this whole matrix, I'm going to get 1, -1, -1. And then I'm going to take 1 multiplied by this matrix to get -1, 1, 1, and then again 1 times -1, 1. So that's where the diagonal elements come, and off-diagonal elements are all 0 value. And so if I apply the symmetry operation, I ask which of these tensor elements recovers a value of -1 when multiplied by this symmetry operation. And that corresponds to, you can see very clearly, it's pretty clean in this case. It's alpha xy, alpha xz, alpha yx, and alpha zx. So that's all well and good. That tells us where the -1 came from for this symmetry operation, but we still have 2 more symmetry operations to go, and those give you, so this is the one we did previously. If we go through the exact same operation for a different symmetry matrix for the green, that is the sigma xz, and the sigma xz, you'll remember, is 1, 0, 0, 0, -1, 0, 0, 0, 1. And then the orange is a C2, which gives us -1, 0, 0, 0, -1, 0, 0, 0, 1. And when you look through this collective set, something that has each of these eigenvalues as a product of this of these symmetry operations, you can see that the only one that satisfies all of the requirements and recovers the correct value for the particular values as stated in the character table are sigma xz and sigma zx.